Hello, I wanted to give you the opportunity to view the office hours review sessions that took place on Tuesday. Just in case you weren't able to make it, or even if you went and you want to see this work again. So here we have a mechanism. This is from the review session, preceptor review, an exam that took place a year ago. We have a mechanism and an overall reaction, and we're asked to find the overall rate law and explain what factors will increase the rate. So we could write the rate law directly from the slow step. We know the slow step here is the first step, so we can write based on the molecularity of CH4, first order. And that means that the rate constant, which is A times minus EA over RT times CH4, we tend not to write the rate law this way, but we can. It will help us explain what factors increase the rate. It's going to be three factors. It's going to be the activation energy, going to be the temperature, going to be the concentration of the species in the rate limiting step. So if we want to increase the rate, we could lower the activation energy by adding a catalyst. We could increase the temperature, or we can add more CH4. So those are the three different ways we can increase the rate of the reaction. Given the reaction, draw the potential energy versus entropy curve diagram, delta G versus T curve, and the equilibrium constant with T curve. And then we can explain the signs of delta H and delta S of the reaction and determine if directionality and extent are temperature dependent. So by looking at this chemical reaction, we see that the products contain AA bonds, so we'd expect it to be endothermic. So delta H is positive, and we'd expect delta S to be positive since 4 moles of gas in the products, but only 2 in the reactants. Based on the signs of delta H and delta S, we would construct a PEC diagram like this, with reactants favored at lower temperatures and products favored at higher temperatures. We also see the directionality. They're the same signs, so directionality will change with temperature. And with K versus T, the extent is always temperature dependent, but we see that K will be less than 1 at low temperatures and greater than 1 at higher temperatures. So product favored at higher temperatures. Directionality is temperature dependent, and extent is always, Kc is always temperature dependent. You may not make more product than reactant at some temperatures, but extent is always temperature dependent. Alright, so sketching the concentration of methane versus time, we know that the overall rate law is first order in methane. This would give us an exponential decay. So if we made a plot of concentration of CH4 versus time, it would look exponential. It would start off at some value and then decay down in a curvy exponential sort of way. Drawing the energy diagram for this reaction, we need to take into a couple accounts. First, what are the signs of delta H for each of the steps? We would assign it as plus, plus, minus, given that methane is 1 particle is breaking apart into 3. And step 2, 1 particle is breaking apart into 2. And then step 3, we would assign as exothermic, which is 2 particles making 1, with an overall positive delta H. So the way we would do this is show 2 endothermic steps, 1 exothermic step, but overall has to be endothermic. So it would have to look something like that. And then the next thing is to put in the activation energies based on the slow, fast, fast mechanism. So the first step would have a high activation energy. Then the next 2 steps would be lower. So activation energy for step 1 is expected to be the highest. Okay, so we're going to sketch the rate of the reaction versus the concentration of methane and for CO2. So we make the graphs. So we know we have a first order overall rate in methane. And since CO2 is only in the fast step, we see that is not in the overall rate law. It's zero order, right? As in it's a constant value. That means it's a straight line, while for methane, it's a straight line with a positive slope starting at the origin and going up. The slope is equal to K, right? Because the rate is proportional to the concentration, the first power. And for the rate versus CO2, it's a straight flat line, meaning we could double, triple, quadruple CO2 and it doesn't change. Next question was asking how increasing the temperature will affect the extent of the reaction and the rate. So let's take a look. Well, anytime we want to know whether a reaction is affected in terms of extent, what we need to know is it an endothermic reaction or is it exothermic? We know it's endothermic. So the extent, Kc, is proportional to products over reactants. That means as we increase temperature, we're going to favor more products. Kc is going to increase, so extent will increase. The rate of the reaction will always increase with temperature, with increasing temperature. Okay, so it really depends for extent whether we're talking about an endothermic reaction or an exothermic reaction, while the rate always increases. The next question asked about what happens to the addition of a catalyst. How will this affect the reaction rate and extent? Catalyst lowers the activation energy. So at a given temperature, K is going to increase if we lower the activation energy. So K will go up if EA goes down at a given temperature. Catalysts do not change delta H reaction and delta S reaction because they cancel. They're present on both sides of the reaction. If that's the case, then Kc, the extent, does not change since delta H and delta S are the only contributions to Kc. So we see a catalyst will increase the rate, but it does not change the extent of the reaction. How Kc, what will happen if we double the amount of CH4 and CO2 on the extent of the reaction and the rate? Sorry for the wording. All right, so let's take a look. If we double methane, there's going to be no effect on Kc, as we've talked about in class. But since it's in the overall rate law and it's first order, we expect the rate to double. If we double CO2, we expect no change, again in Kc, but in this case we expect no change in the overall rate of reaction. Okay, so now we have some data. We have to be able to find the order of the reaction. And so we have to be able to determine is it zero order, first order, or second order based on whether the graph is linear or whether the change in concentration with time is constant, the change in delta Ln of the concentration is constant, or the reciprocal of the concentration is constant. So first it asks at what temperature is the reaction product favored. So we have delta H is less than 0, delta S is less than 0. It's favored at low temperatures, but what does low temperature mean in this context? It means when delta G equals 0. So the temperature is the ratio of delta H to delta S, and we plug this in and we get it's 586 Kelvin. So for the context of this reaction, 586 Kelvin means low temperature. So if you're below 586, this reaction is product favored. So lower than 586. Now, what's the order with respect to CO2 given this data? So this is where we have to make a table of first, second, and 0, first, and second order. And what we're saying is the rate of the reaction in the first time points the same as in the last time points? Right? Is this the same? We're going to ask the same question for first order, except it's going to be true. If it's first order, it's going to be the ln, right? The change in the ln of the first two data points divided by minus 40. Is this the same as the last two data points? And we plug that in. And now for the second order, we have to look at the reciprocal. And we say, is the reciprocal of the concentrations for the first time point the same as the difference in the reciprocal for the last time point, last two time points? Because each of these are a measure of k, and k will be constant with respect to each of these orders if it is the order. So let's take a look. So for zero order, we plug in the numbers and we say that no, 8.9 times 10 to the minus 5, which is what you get for the first calculation, is not the same as 2.3 times 10 to the minus 5, so it's not zero order. First order, we plug these numbers in, and yes, 0.011 is equal to 0.011, so yes, it is first order. For completion, we look at second order, and no, minus 1.38 is not the same as minus 5.2. So we have determined that the order of the reaction is first order, so the rate is K times the first order CO2, which is 0.011 times CO2 to the first power. That is the rate law. Question now is, how much time is necessary for 90% of the sample to disappear? So first order, we can plug this in. We know K, and we're solving for time. For 90% of the sample to disappear, that means that only 10% remains. So there's 10% left of 1 times 10 to the minus 2, or 1 times 10 to the minus 3. We plug these numbers in to the integrated rate law, and we can solve for time. So it's the ln of 0.1 divided by 0.011, and we get 209 milliseconds. Keeping in mind that whatever units time is in, that's what our value is going to be in. So using the integrated rate law, we can answer this question once we have the analysis of K. The next question asks, what's the activation energy given this data set? So we know that the rate constants, given any two rate constants and two temperatures, we can calculate the activation energy. And keep in mind that if given any four, K1, K2, EA, T2, T1, we can always find the fifth one. In this case, we can plug in the ratio. We're given the ratio of Ks. We know those Ks. They're given the table. We can take the ln of both sides to make it easier for us to calculate. And we get the ln of 2.26 times 10 to the minus 2 divided by 10 to the minus 4.44 times 10 to the minus 2 is EA times the first temperature corresponding to 226 and the temperature corresponding to 4.44. Solving for EA, we get the ln of 0.509 times minus R divided by the difference of the reciprocal temperatures. Plug this in and we get 55 kilojoules per mole. So the activation energy for this reaction is 55 kilojoules per mole. So let's just make a summary of zero, first, and second order, which is the focus of Unit 3, Module 3 and Module 4, either with mechanisms or looking at data. The rate is either K, which is for zero order, K times the concentration to the first power for first order, or rate is equal to K times the concentration to the second power. The concentration versus time is a straight line for zero order. Concentration versus time for the species is a curvy exponential. And the concentration versus time for second order is also curvy. It just happens to be slightly different than the exponential, but it still resembles it very much. The only way to distinguish the first order from the second order is by using the linearization of the rate law. So here, the rate versus concentration for a zero order and the first order and second order is shown here. So for zero order, it's a straight line with the value of K. In first order, it's a linear plot shown at the origin with the positive slope, with the slope being K. And for the second order, it's a parabola with something K and the concentration squared. So with this is what we went over in the office hour. I hope that this resolves any questions you might have, and good luck on the exam.